Thank you. And thank you all for being here. I'm especially appreciative of your presence because this is the very last talk of the paper session. So, so this talk is going to be about some very efficient algorithms that we have developed for the reconciliation problem under a model that accounts for gene duplication, horizontal gene transfer, and loss. And in fact, in the very previous talk in this room, Professor Lineal mentioned that they had restricted their analysis to eukaryotes because, analyzing prokaryotes was pretty hard because of horizontal gene transfer. And that's exactly the kind of thing that we want to address here. We want to deconvolute the process of horizontal gene transfer, detecting, horizontal gene transfer and so on, so that bacterial analyses are as simple as eukaryotic analyses. Okay. So the basic fundamental problem that we are trying to address here is this. Given a gene family, what is its evolutionary history? So gene families, of course, start their life as a single gene in some ancestral species. And there, they're affected by evolutionary processes like speciation, gene duplication, gene loss, horizontal gene transfer. And so let me illustrate that with a little diagram here. So let's say this is a species tree on 4 taxa, A, B, C, and D. And let's consider the evolution of some gene G that starts out in this ancestral species X. So it's evolving along the topology of the species tree now. And let's say at Y, it duplicates. Okay? So now there are 2 copies of that gene in the lineages that descend from Y. Let's say one of the copies in B gets lost, another one in C gets lost, and then furthermore, there's a transfer, let's say, from D to C. Okay? Now, if you were to take the genes of this gene family and construct a gene tree on it, you would see something like this, right? That's the gene tree constructed on this gene family. And the task of reconciliation is that, you're given the species tree, you're given the gene tree, but you want to infer this whole evolutionary history. You want to figure out exactly how you got that gene tree. What were the duplications, losses, and horizontal gene transfers? And so to infer this, basically it is sufficient to infer the embedding of this gene tree into the species tree. So basically what you want to do is for each internal node of the gene tree, you want to figure out exactly where it maps in the species tree. So this node, for instance, I know maps to X, this one maps to Y. And you want to figure out the event. Okay. Great. And you want to figure out the actual event that is represented by that node. So this one is a speciation, delta represents duplication, theta represents transfers. Right? So basically for each node you want the mapping and the event. And that's sufficient to infer this. So basically, the input is a gene tree and a species tree, and the output is exactly this reconciled tree. So how do you actually solve this problem? The typical formulation is a parsimony one, where you assign costs to each type of event. So you have a cost for duplication, a cost for transfer, a cost for loss. And then you want to find the reconciliation that minimizes the total cost. So for a given reconciliation, for let's say this one, it's pretty easy to compute. So if for this given reconciliation, and if say my costs for loss, duplication, and transfer are 1, 2, and 3, then I know that this reconciliation implies 1 duplication, 1 transfer, and 2 losses. So I can compute the reconciliation cost to be 7 in this case. And the task is to actually find the optimal reconciliation that minimizes this cost. So why do we bother with this problem at all? Why study reconciliation? So obviously there is this immediate application, right? You want to understand gene family evolution, and you can't do that without understanding the history of speciations, duplications, transfers, and losses. Besides that, you can use it for dating gene birth. So, for instance, you have as part of the reconciliation, you know where the root node of that gene family tree actually maps to in the species tree. You can use that now to date your gene families. You can infer orthologs and paralogs. So the moment you have a reconciliation, the problem of inferring orthologs, paralogs becomes trivial, right? Because given any pair of genes in this tree, let's say A1 and B1, I can immediately say that this was a it's a paralog because its most recent common ancestor is a duplication node. Similarly, A1 and C1 would be orthologs because their most recent common ancestor is a speciation. Right? In addition, there are some more advanced applications. For example, gene tree reconstruction. So reconciliation is a very nice way of incorporating information from the species tree into the gene tree. And gene trees are notoriously hard to reconstruct because you can have some gene families have very low rates of evolution or very high rates of evolution or very short sequences. So incorporating information from the species tree through reconciliation gives you a way to construct more accurate gene trees. Now, similarly, you can do whole genome species tree reconstruction. You can construct gene trees on a bunch of gene families from across the genomes of your species of interest, and then try to find the species tree that best reconciles all of them. And this is known to be a pretty effective method. Now, the problem with this is that all of these powerful applications have only been developed in the context of eukaryotic systems, and particularly in multicellular eukaryotes. And that's because in those cases, you can actually ignore horizontal gene transfer. And once you ignore horizontal gene transfer, what happens is that the reconciliation problem is greatly simplified. You have linear time algorithms for computing optimal reconciliations when there is no HGT, only duplication and loss. And so you can afford to do all of those nice applications like accurate gene tree reconstruction, species tree reconstruction, apply to very large gene families and so on. But for the general reconciliation problem that we are studying here, one that includes horizontal gene transfer, the fastest algorithms have cubic time complexity. So specifically, it's order mn square, where m is the number of taxa in the gene tree, n is the number of taxa in the species tree, which is really slow. And as a result of this, you cannot really study large gene families. You cannot do gene tree reconstruction because this process involves evaluating thousands and thousands of candidate gene trees against the known species tree in the reconciliation framework. And similarly, you can't do species tree reconstruction because there you have to find the species tree by searching over a very large tree space. So this also involves reconciling millions of candidate species trees with the input set of gene trees. So our goal really is to be able to enable these very powerful applications of reconciliation to the rest of the tree of life, right? So right now, this is where we can do these things. These are multicellular eukaryotes. For the remainder of the tree, there's nothing. And to be able to do this, we need to fix the bottleneck. The big bottleneck here is that the algorithms are too slow. So we develop in this work, we basically developed faster algorithms. And later on in follow-up work, we've also actually applied these algorithms to accurate gene tree reconstruction. And I'll talk about this briefly towards the end of the talk. So here is a summary of our results. So if your species tree is undated, so there's no timing information on the nodes of the species tree, we can solve the reconciliation problem in order mn times. So it's quadratic. It's a factor of n speed up over the current fastest algorithms. If your species tree is dated, so you do have dates on the species tree, meaning that your transfers are restricted to only coexisting species, for that we have an almost quadratic time algorithm, which is mn log n, with almost a factor of n speed up. And we have also considered an extension of this problem where transfer events can have different costs depending on the distance in the tree that they span. And the motivation for this is that transfers are more common between more closely related species. So it makes sense to try and model this in the reconciliation problem, and we have done this, and we have like a simple order mn square time algorithm that can handle both dated and undated trees and distance-dependent transfer costs. And this also is a factor of n speed up over the previous algorithm that tried to do this. All right, so I'll dive a little bit into into what the algorithm looks like. So all three of the algorithms are based on this same dynamic programming structure. So let's say, so this is your input, right? You have the gene tree G, species tree S. And so consider some node G in the gene tree and S in the species tree. And so I'm going to define a variable C for G and S, for any pair G and S, to be the cost of an optimal reconciliation of the subtree rooted at G, so this thing in the green box, of reconciling just this part with the species tree S under the constraint that G must map to S. Right? So it's a sub-problem of what you want to actually solve. And similarly, you'll define a related variable C sub sigma of G and S, C sub theta, delta, and C sub theta, which have the additional restrictions that, that G in addition must be a speciation event, or G must be a duplication event, or G must be a transfer event. Okay? So these are the variables that will populate our dynamic programming table, basically. And this is how you initialize that table. So you'll end up doing a nested post-order traversal. So it's a bottom-up algorithm. You go from the leaf to the top. So at the leaf node, for each leaf node in the gene tree, you know the species from which that gene came. So I know that this guy A1 came from species A. So I'll assign a cost of 0 to this variable here. But for any other assignment for A1, I'll assign a cost of infinity. For B, C, D, or any of the internal nodes, it will be infinity. So that's the base assignment of the dynamic programming table. And also note that basically C for G and S is basically the minimum of C sub sigma, C sub delta, C sub theta, because G has to represent one of these events, speciation, duplication, or transfer. So the idea, like I mentioned, is the nested post-order traversal of the gene tree and species tree. So you look at the gene tree in post-order, and for each node that you consider in the gene tree, do the entire post-order traversal of the species tree. And that suffices to compute all of these 4 values. So basically, the reason why you do this nested post-order thing is that suppose you want to compute C sub sigma of G and S, where this is G and this is S. By the time you are trying to compute this value, you know that you have already computed the values for both children of G. You know for this guy all values of this guy of this node mapping to all possible values of all possible nodes in the species tree. Right? So if furthermore you restrict this to be a speciation node, you know that one of the children of G must map to the left subtree of S, the other must map to the right subtree. And so basically you can now optimize the mappings of the left subtree, right subtree, and compute the reconciliation cost for, like, you can compute C of G comma S. And the source of our speed up is that we can compute each of these values in constant time, which is not completely straightforward. It's easy to do this in linear time, even easier in quadratic time, but it's a bit tricky in constant time. So you continue doing that procedure, and eventually you end up at the root of the gene tree. And the optimal reconciliation cost is, of course, so G could be embedded either starting at the root of the species tree, or here, or somewhere, anywhere. And so you just choose the minimum cost among all possible mapping for the root node of the gene tree. And that's your optimal reconciliation cost. So the extensions of this algorithm, so for dated species trees, what you have is you have a date on each node of the internal node of the species tree, and that restricts where transfers can happen. And so this kind of breaks the very clean structure that we are able to exploit to get our constant time speed for computing the values, and slows down to log n. And basically we have to make use of a dynamic range minimum query data structure and so on, which I won't go into right now. And similarly, for distance-dependent transfer cost, what you have is that, if a transfer originates from here and goes to here, versus a transfer that originates here and goes to here, you'll have a higher cost for this transfer than this transfer, because it spans a larger distance in the tree. So this also breaks the clean structure, and you have to sort of do the computation by brute force. So it slows down by a factor of n. All right, so here's the runtime analysis of our software versus some other state-of-the-art software. So our software for the undated version is called Ranger DTLU. Angst and Mowgli are two existing state-of-the-art software that do the same thing. So we created a bunch of simulated data sets with different sizes, 50 taxa, 100, 200, 500,000, even 10,000, just to see the scalability. So you can see, like for 100 taxa, we can analyze 100 data sets of 100 taxa in 3 seconds versus, let's say, almost 4 hours for Mowgli. If you go for greater taxa size, the gulf becomes obviously even wider. And really, with the existing software, you can't really go beyond 200 taxa, but with our software, we are able to do even like 10,000 taxa trees in under 5 hours. So similarly, for biological data, this is a data set with about 5,000 gene trees or 100 taxa. We can analyze it in about a minute versus, say, 3 hours for Angst and almost 2 days with Mowgli. So it's a huge speed up in practice as well. The impact of this, of these fast algorithms is that you can now really, on your own desktop computer, do efficient, genome scale analyses. You can analyze tens of thousands of gene families in almost no time at all. You can handle gene families that have thousands of genes, which you couldn't do earlier. And you can begin to do these sophisticated applications like species tree reconstruction and gene tree reconstruction that involve performing the reconciliation step hundreds of thousands of times. So I'm going to actually talk about, this is follow-up work which we did after this paper was published. So here we actually applied this algorithm to gene tree reconstruction. And so like I mentioned earlier in the talk, gene trees are pretty hard to reconstruct accurately. But they are very important to construct accurately because even the utility of the reconciliation process itself depends on the accuracy of the gene tree. If you have a wrong gene tree, you infer wrong ortholog, wrong paralog, and so on. So for eukaryotes, there's a bunch of methods that have been developed based on just a duplication loss reconciliation model. But none of these are applicable to prokaryotes because of the problem of horizontal gene transfer. So we wanted to fix that. So basically, we chose the best performing program for eukaryotes, which is Treefix, and extended it by swapping out basically the reconciliation module that uses duplication loss for our module that can handle duplication loss and transfer. And we have a new program called Treefix DTL. So the task is to basically figure out how much better we can do with our module than what Treefix can do on prokaryotic data. And the idea here is pretty simple. The idea of Treefix is that it builds a cloud of trees around the maximum likelihood tree. This cloud of tree contains trees that are statistically equivalent in terms of to the maximum likelihood tree. And then you reconcile each of them with the species tree, and the assumption is that the one that has the lowest reconciliation cost is the more accurate reconstruction. So we did like a pretty thorough simulation study with trees of 50 taxa with low, medium, high rates of duplication, transfer, and loss, different rates of evolution, different sequence lengths, and we reconstructed the maximum likelihood trees by using RaxML. And here are the results on just the data sets with the low rates of duplication, transfer, and loss. So the bars represent, so the first bar is RaxML, second bar is Notung, and third bar is Treefix. So Notung and Treefix are the two programs for eukaryotes. Treefix DTL is our program. And the y-axis represents the error rate in the reconstructed gene tree. So this is the number of branches that are incorrectly inferred in the gene tree. So as you can see, RaxML obviously has the highest error rate. Notung and Treefix fix it to some extent, but if you look at Treefix DTL, it's much, much better than the eukaryotic programs. And the similar trend you observe even for the shorter sequences. And the same trend for medium and high DTL datasets, which I'm not showing here. In fact, for the high DTL datasets, you often see that Notung and Treefix will make the results even worse than RaxML. Similarly, so here we test the impact of the incorrectness in the gene tree reconstruction on the actual reconciliation. So what we are doing here is we compute the reconciliation cost for the RaxML trees and the reconciliation costs for the Treefix DTL trees and divide them. So here you can see for the low TTL data sets, RaxML is inferring more than twice as many events, like more than twice as many losses, duplications, and transfers as the corrected tree, which is quite ridiculous. So basically, it's telling us that between 1.5 and between 50 and 100% of the events are sorry, between 25 and 50% of the events are bogus, basically, if you do not error correct your gene trees. So it's very important to error correct gene trees. So to summarize, we basically developed very fast algorithms for the reconciliation problem with duplication, transfer, and loss. And these algorithms enable, for the very first time, all the very powerful applications that have traditionally been used only in eukaryotic systems. So we've also demonstrated the utility of our algorithms for accurate gene tree reconstruction. And it's also worth mentioning that these same algorithms apply without any change to other application domains like host-parasite coevolution. So for instance, so in host-parasite coevolution, the host tree becomes a species tree, the parasite tree becomes a gene tree, like parasite switches. So host switches are like transfers, independent speciations are like duplications, and so on. So there's a one-to-one mapping. And so implementations of all these algorithms are freely available here in case anybody wants to use them. And so I'd like to acknowledge funding from NSF and NIH to my postdoc advisors, Manolis and Eric. And this presentation was made possible by a fellowship from the travel fellowship from ISCB. And thank you for your attention. Be happy to take questions.